Okay, so what I wanted to do now is just basically sort of overview how the course is going to run. So the main website is, give me a second. So I'm having to work on my laptop. I normally have a couple of big screens, but for various reasons, I am on my laptop. So give me a second. Sorry about this. So the main, okay, so if I now share this screen, okay, so under the training page, you will see the course that we're on, Upcoming Training Advanced MPI. If you click on that, you'll see the general blurb, but there's a course materials link here. So if we go to that, it's a fairly bare bones. I wouldn't recommend. Well, you can clone this repo if you want. There's a lot of. It's probably better just to look at it online. So I'm just going to give a brief overview of the ARCHER2 training here. But the next thing I was going to do is to do a quick quiz, which I think is fine. And so it's just a way of kind of talking about MPI, getting an idea of people's interest, and just answering a few questions. So if people could go to that link, I will put this in the chat. So if I go to the chat. So you should see a question. So this is just, so I'll wait for people to get onto that page. But I think the important point I'd like to say is that the well, I'll wait till a few people have logged on, and then I will. So if I so hopefully you should see. Okay, so the important point about these questions is they're really just to promote discussion at the start of the course, but it is important. None of the answers I have provided here are stupid answers. So don't, if you don't know the answer, just guess. I'm interested in what people think, but none of the answers are stupid. It's this is really to promote discussion and start thinking about things. So just just say what you think. But as I said, it's hopefully it's a reasonably challenging quiz, and don't all of the answers are potentially correct answers for a generic message passing system. So if I said I'm going to teach you about message passing, here's a question. All of these answers, most of the answers to the questions are actually potentially correct answers. But what I'm asking here is, what is the answer for MPI? Okay. So there's a couple more people may want to join or answer and have a guess, but I'll just go to the quiz now. So I'm trying to juggle too many windows. Okay, so I will do show results. Okay, so people did very well. This is I'm very pleased that nobody said create the 4 parallel threads. I'm normally not a pedant, But in terms of MPI, it is important that MPI is based on processes, not threads. OpenMP, if you've done OpenMP, is threads-based programming. A lot of people think it creates the 4 parallel processes. There have been message passing systems where that happened. There was a message passing system back in the late 90s, early 2000s called PVM, Parallel Virtual Machine, where when you called the PVM setup routine, PVM, and it did launch the processes. But it doesn't actually start program execution. The important point about MPI is when you launch a program, when you do MPI run, what MPI run does is it launches multiple copies of your program. And so actually all the MPI init does is very good that most people got it, enable the 4 independent programs subsequently to communicate with each other. So the important point about MPI is that it's parallel from the start. So that was just a warm-up question. I'll go to the next question. So I'm just sort of. So I mean, these are just fairly. I'm going to ask fairly standard questions. Sorry, I'm going to ask questions about fairly basic functions like send and receive. If you call MPI receive and there's no incoming message, what happens? Does it fail with an error? Does it report there's no incoming message? Does it wait until a message arrives, potentially forever, or does it time out after some particular delay? As I said, if you don't, it's all anonymous. I have no idea who's answering here. If you don't know, just have a guess, because it's interesting what people think. Because all these behaviors are potential behaviors, just that MPI has a particular. And if you have any questions or you disagree with what I'm saying, please stick it in the chat. So I'll just wait. One more person. Okay, so most people have answered. Checking something. So yes, so most people got the right answer. In MPI, the receive waits until the message arrives, which often surprises people. So both B and D are reasonable answers. The receive. So you can imagine an MPI, a message passing system that says, like, I haven't received a message for an hour. There's clearly a problem here. And in fact, you know, that could be because there's been if MPI were fault tolerant, if MPI had fault tolerance in it, then you would want this behavior. You'd want MPI to say, well, if I've not received a message for an hour, clearly the node that's the process that's sending me the message has died. Okay, and you would report there's been some problem. However, MPI is not fault tolerant. MPI has almost zero ability to cope with faults. So MPI assumes that your program is 100% correct, and also the hardware is 100% correct. So it will wait forever. And actually, the difficult question is, if there were a timeout, what would it be? You know, you could launch a program and set up a receive for the outcome of calculation, which might take a week to run. So there again, PVM, which was a message passing system built to run on clusters of desktops and workstations in an office, for example, where there was always a problem that someone might come in and switch their laptop off. And so it had fault tolerance, it had timeouts and stuff like that. MPI doesn't. MPI assumes that your program is 100% correct and that the hardware and the software is 100% reliable. Therefore, it assumes that there will be a message coming in. But so that does sometimes surprise people. So MPI, this is slightly confusing about MPI. So people are doing very well here. Maybe I do this quiz on my own course sometimes, and maybe people have seen this. If you call MPI synchronous send and there's no receive posted, which of the following are possible outcomes? So synchronous send is MPI's one of MPI's message passing models. It's synchronous. It's analogous to making a phone call. So this is one of the problems, but well, the difficulty of MPI, something we'll talk about on the course, is that MPI has a number of different modes, and I'll mention them here. There's synchronous, buffered, and standard, and they are slightly confusing for possibly legitimate reasons. But if I was to call synchronous M, which is MPI's equivalent of making a phone call, and there's no receive process, which of the following are possible outcomes? Not necessarily what happens, but what are the possible outcomes of that send? I'm actually going to ask the same question for the 3 MPI sending modes. standard, buffered, and synchronous, buffered, and standard. And again, this is something which is often misunderstood in MPI, and people maybe don't quite pick up the details on their first course. But if you're going to understand and write optimal code, it is important to understand how these actually operate. Although at the end of the day, they may achieve the same thing of sending data from A to B, they are different semantically and in the way they're implemented. So I'll wait for maybe one more person to have a guess, and then we can. Okay, so there are ways in which D is true, but synchronous send is like, so people are doing very well here. The send waits to the receiver posted, potentially waiting forever. So synchronous is making a phone call. So you pick up the phone and you wait for the person at the other end to respond. So people are doing very well. So people with very high MPI knowledge here, it's very good. The next question is exactly the same question for buffered send. Sorry, previously okay, there's slightly not exactly the same answers, but if you go now some of these questions may have more than one answer, and I think you can select multiple answers. If you call MPI asynchronous send, MPI send, and there's no receive posted, which of the following are possible outcomes? So MPI send is synchronous, and that's why if there is no receive, then you wait forever and your program will deadlock. MPI send is asynchronous. And so what do you think happens here? Which of these are possible? So when there are multiple answers, I'm not exactly sure how this system copes with it, but let's show the results. So okay, so this is not trick. So most people have actually done very, very well here. So the important point about send, buffered send, buffer send is asynchronous. It's like posting a letter. It's a fire and forget method, and so this has two effects. One is that the message is and buffered is there to make it clear to you that a copy is taken. So the MPI will buffer this message somewhere, and that means that the message is stored and delivered later on if possible. But the corollary is F as well. The sending process continues execution regardless of whether a message is received. This is like sending an email to somebody. You just carry on your day. However, B is also a possible answer. The send fails with an error. So can anyone think why that might? In fact, now actually, the first time I gave this course, I didn't actually have that as an option. But sorry, it was there, but it wasn't given as a correct answer, and someone pointed out. So the message could fail with an error. Does anyone know? Guess why B? No one maybe have it in the chat, so you should see the chat or in audio if you want. No. So that okay. Yes. So Sherman, you're absolutely right. Sherman's right. Yes, if you sent to the wrong rank, you would get an error. So I should say I'm assuming that all other things are correct. You're absolutely right. Yes, you can run out of buffer space. So in MPI. Asynchronous, you rarely see programs using asynchronous send, buffered send. It's rare because it's nasty. And the reason is that MPI says if you call an MPI buffered send, you are mandating, you are demanding that the message is buffered. You are saying you must take a copy of this message, okay? So just to take a step back, what you're saying is I want to send this message asynchronously. I want to send the message and I don't care, just send it off, okay? The problem is with that is that you have a send buffer, say a kilobyte of data you want to send, and you're telling MPI, please send this, but don't tell me when, if or ever it arrives, just send it. Later on, you're going to want to reuse that buffer space because you don't want to leave that space untouched for the rest of the program execution. But how can you know when you're allowed to reuse that buffer space? The send buffer, because you don't know if the MPI has delivered the message or not. So if you think about it, the only way it's possible to implement an asynchronous send, a fire and forget protocol, is if MPI takes a copy. And that's why in MPI, the asynchronous send is called buffered send. It has to take a copy. However, where is that copy taken? Where does the memory come from? Well, in MPI, it's up to you to provide it. And there's a very, very nasty routine called MPI buffer attach, where you say at the start of your program, you malloc some space, and you say to MPI, okay, I've reserved a megabyte of space for buffered messages. That's where you should put them if I do buffered send. The problem is if you send one message which is larger than a megabyte, or multiple messages which queue up, that buffer space could overrun. Okay, so and so MPI send, although programming with asynchronous send would be nice, you would have less concerns about deadlock. The way it's implemented in MPI is rather nasty, and very few people use MPI send. I mean, in fact, I will maybe do a I'm going to do a little poll to see if people have used it. So can you see the responses? I don't know if I can't remember if this. Yes, you can see. So just out of interest, who has used MPI send? Can you maybe just? Okay, Theo. So I know you can do. You can. Does your audio? Do you want to describe? Well, I think we can do it in the chat. I'm just interested in what the situation was. Okay, fine. Okay, fine. Okay, there you go. Fine. There you go. Fine. I understand. There we go. Thanks. Okay. So the next question is, if I can find where I am now. So standard send. Okay. So most people program with standard send. Okay. It's the standard send. It's the one you would expect to use. However, it is not quite as simple as you might think. So this is exactly the same question as the previous. I have exactly the same answers as the previous two. But which of the following are possible outcomes? I'm sort of asking here, do you think MPI standard send is synchronous or asynchronous? This is sort of what I'm asking here via the back door. I said the answers aren't obvious at all. And this is something which, well, I'll explain later, that I did not understand an MPI for quite some time. Okay, so we've got quite a lot of answers in. Anyone else want to guess? But I will show the results. So, the important point here, so people have done very well here. The important point is that, well, MPI send is allowed to be synchronous or asynchronous. And this is the source of quite a lot of confusion, because a lot of people assume that MPI send is asynchronous, but MPI send is allowed to be synchronous or asynchronous. And MPI can do what it wants. So in principle, MPI could say Monday, Wednesday, Friday, I'll make MPI send synchronous, and Tuesday, Thursday, Saturday, Sunday, I'll make MPI send asynchronous. However, that's not what it does. What it actually does is so MPI send can be synchronous or asynchronous. So you might think that the correct answers here were the union of the correct answer for the previous two questions. Okay. However, they sort of are. So if MPI send decides to be synchronous, then you get the behavior of C. The send waits until a receive is posted, we're potentially waiting forever. If MPI send decides to be asynchronous, you get D and E. The message is stored and delivered later on if possible, and the program continues execution regardless of whether the message is received. However, what you don't get is B, the send fails with an error. And the reason is what MPI is doing here is it's saying, look, I'm allowed to be synchronous or asynchronous. What I will do is I will reserve some internal buffer space to buffer the message for standard send. This is not the buffer space as the user supplies with MPI buffer attached. It's some internal buffer space over which you don't have direct control. You may be able to mess about with it with environment variables. So MPI says, so for what MPI, for small messages, MPI decides to be asynchronous. So MPI send, it buffers the message, returns control to you, and then moves on. For large messages above this buffer size, which you don't know what it is, but you could find out by experimentation or looking at the manual, it says, okay, I don't have enough buffer space, so I will become synchronous. So that's why B is not the, what MPI is doing is it's trying to be buffered, it's trying to be asynchronous, but if it can't buffer the message, rather than failing like B send does, it says, well, MPI, I'm using MPI send, I would like to be asynchronous, but I can't, so I will become synchronous, I will wait. And then later on, maybe everything's cleared up and the next MPI send could become asynchronous. So this is slightly confusing, but it is now, yeah, it's slightly confusing, but we will see when we do the sort of MPI internals that this allows MPI to do some sort of internal optimization. Basically, MPI can optimize for small messages, which is good. But be safe so that it can still deliver large messages. So that is that's slightly okay. Just a brief question here. The MPI send routine has a parameter count. What does this mean? So when you do a receive, you do MPI receive, buffer count, data type, whatever. What does the count mean? Is it the size of the incoming message in bytes? Is it the size of in items, e.g. integers? Is it the size of the buffer you've reserved for storing the message in bytes, or the size of the buffer you've reserved for storing the message in items? So anyone else just wants to take a guess? Okay, so I'll look at the answers here. So okay, so this is actually, although anyone who's programmed in MPI has called MPI receive thousands of times, so MPI doesn't like to talk about bytes. So MPI tries to be architecture neutral, and that means that once you start mentioning bytes, then you're not architecture neutral. One machine may have 4-byte integers, another might have 8-byte integers. So now B is a perfectly reasonable answer, because in many programs, then you know what the size of the incoming message is. So for example, if you're doing a standard regular domain decomposition, you're doing halo swapping, you know that your neighbor's halo is the same size as your halo because they're abutting. So if your halo is 100 integers, then so often the incoming message is often the count is the size of the incoming message, but technically that's not what you're saying. When you issue a receive in MPI, if you say MPI receive x 10 integers, what you're saying is, I want to receive a message from somebody, and I have reserved enough space for 10 integers. Okay, that may, in your program, also be the size of the incoming message, but technically you're just saying, I want to receive a message, and I've reserved enough space for 10 integers. Okay, so the obvious subsequent question is, what happens if the incoming message is larger than count? Okay, you said I do an MPI receive, and I said I reserved enough space for 10 integers. What happens if the message coming in is 20 integers? So this is maybe something you've never actually encountered, but so people just want to take a guess, and we can have a look. Okay, so again, all of these are perfectly reasonable answers. Okay, none of these, all these perfectly reasonable answers. However, it's interesting. Okay, so I think what this quiz is illustrating is that in MPI, send and receive are surprisingly not complicated. They actually don't quite do what you think they do often. So what actually happens, the receive fails with an error. So MPI is trying to be safe here. It's saying David's asked for a message and said that he's got 10 inches of buffer space. The incoming message is 20, so I can't do it. Now, so the answer is not C, because MPI does try and be reasonably safe in terms of making your code correct. Actually, I don't know if you've MPI is typically not very good in reporting errors. Typically, MPI just dies. This is one of the cases we do have to normally get useful error. It will say error message truncated on receive or something like that. But it will crash. It will crash. And so when I say wet with an error, technically when MPI detects an error, it calls an error handler. But the default error handler is called the MPI errors are fatal. So even for the most trivial error, MPI will crash and burn in a heap. Now, so it's not C. So only the first count item received is an interesting answer. So a lot of people who come from a more computer science background, who've done communication protocols before, have come across pipes. So this is what you'd expect if there was a pipe. You're pumping data in at one end, and then you can choose to receive it at the other end, okay, in chunks, okay? So it's a continuous flow of data. So D would be exactly what you'd say if your mental model of message passing was a pipe model. Now that's not the way that MPI works. MPI works on individually matching a send with a receive. So the problem with D is, if you receive the first count items, what would happen with the other count items? Would you expect the next receive to? It gets complicated. So MPI requires every send to have a matching receive, and it needs to match in its entirety. Okay, so as I said, C and D are both perfectly reasonable answers, but they happen to be not what MPI does, and so MPI will in that case say I can't do it. Okay. The next obvious question is, now what happens if the income message size n is smaller than count? Okay, I've called an MPI receive of 10 integers. The receive returns. Technically, at that point, all I know is that a message has come in which was smaller than 10 integers or smaller. Now, again, in your program, you may know that that meant the message was 10 inches. But in general, it just means a message came in which fitted in the buffer. Okay, so if the incoming message of size n is smaller than count, what happens? Actually, I've given away some of the answers here by wittering away. So I'll look at the answers if other people just want to have a quick guess. So I kind of gave, I was speaking to the next question, apologies. Okay. So the correct answer is the first 10 items are received. The received doesn't fail with an error. The reason is that MPI is written to allow you to write programs where you don't know how big the messages are. And although if you write regular, fairly static programs, you often know there are situations where you don't know how big the incoming message is going to be. So you need to be able to, in general, receive messages where you don't know what the size is. Now, you may have an upper bound. I know that this message can't be bigger than a megabyte, and that happens in, for example, imagine you were doing a crowd simulation. You're doing a simulation of people leaving a building to check for fire regulations. Can all the people get out in under 5 minutes, for example? You might have divided your building up into domains, and you want to do a halo swapping. What you want to do is you want to exchange information with your neighbor, with all the people who are within 2 meters of the boundary, for example. The point is you don't know how many people are within 2 meters of your neighbor's boundary. You don't know the information of how many people your neighbor is going to send. So that's why MPI allows you to receive messages of an unknown size as long as it fits in the buffer. The reason why C and D are perfect, the reason why D is not the answer is, I've thought about this. I think that the main reason is efficiency. Okay, MPI is written to be efficient. Imagine I did an MPI receive and my buffer was 1 gigabyte long and I received a message of 1 byte. If MPI went away and spent 1.5 minutes zeroing the rest of the gigabyte, you would be a bit annoyed. So I think it's really, there is no need to zero the data, so it doesn't do it. I mean, there are also situations where you might not want the data zero, but I think the real reason is, zeroing data takes time, so it doesn't do it. Okay, that's right. The next question is, so this is kind of, okay, we've issued an MPI receive, we've said our buffer is 10 inches long, a message has arrived, and as I said out of step previously, technically all we know is that a message has arrived which is 10 inches or smaller in size. But think about that particle, that crowd simulation. Okay, my neighbor sent the information on a certain number of people. How many people were? How big was the message? So how do you actually know how big the incoming message? Again, you may never have had to do this because your messages may always have been of fixed size. But the question here is, how do we tell? Okay, so the correct answer is stored in the status parameter. The status parameter gives you information on the message that was actually received. So often we use it if we have done a wildcard. So if you do an MPI receive from MPI any source and a message comes in, you don't know who it came from, and that will be stored. But that information will be stored in one of the status. Often people with MPI status ignore, which I don't like, I have to say. So MPI cannot tell you. That would be difficult. If MPI couldn't tell you, it would be difficult. It would be hard to write a correct program. As I said, MPI is designed to allow you to write correct programs where the size of the message is not known. So A and D are perfectly reasonable answers. However, you could do it via the tag, but MPI says you don't have to. It's stored in the state, so it's done automatically. You could specify it as the tag. That's perfectly correct. However, there's no need to, because it's in the status parameter. The value of the count that the receiver is updated, that would be nice possibly, but if you think about it, the prototype for, if you're a Fortran programmer, that might be possible, but for a C programmer, the MPI prototype for MPI receive is would not allow that, because the prototype for MPI receive is, if I just put it in the chat, sorry, I'm losing my, the prototype for MPI receive is this, and so you'll see that the count is passed as an integer, so it's passed by value. So although it might, so the way the prototype is designed, it's actually not possible for MPI to update the count. What actually happens is it's returned in the status parameter, which is passed by reference, and that is updated. Okay. So final couple of questions. And actually, just briefly, for technical reasons, it is stored in the status parameter, but it's slightly hidden away. But anyway, so this is the final couple of questions. It's kind of wildcardy questions. Some MPI collectibles specify both a send type and a receive type, e.g. MPI scatter, send buff, send count, send type, receive buff, receive count, receive type. The vast majority of times you see the call used in practice, we have send type equals receive type and send count equals receive type, receive count. So 99% of the time you see people use scatter, broadcast, not broadcast, but they're definitely scatter, and these routines, all to all, gather. You will just say, I'm scattering 10 integers or receiving 10 integers. So however, so that seems to be like overcount. That seems to be like over specifying. Why, with MPI scatters, we have to specify both the send count and the receive count and the send type and the receive count? Surely they're the same. So why does MPI make you specify both types? And this is talking about, well, I'll ask you. This is really talking about message matching in MPI. When does a message match? Another one is slightly more subtle than you might think. I heard a beep there. Is there a message? So if you've joined a little bit late, we're just doing a quiz. It's almost finished, so you might not be able to join the quiz, but you can at least follow on the answers. It'll be finished in a couple of minutes. So I think the beep was somebody joining. I thought it was somebody asking a question. But okay, does anyone last wants to take a guess? So let's share the results. Okay, fine. So people have done very well here, actually. So A would be nice, so it can check at runtime that you haven't made a silly mistake, but actually MPI doesn't check anything. MPI is written for efficiency, and checking that you haven't made a silly mistake would take time. So MPI tends not to do that. So we do type conversion, that would be nice as well, but MPI doesn't do that. MPI doesn't do type conversion of that type. So C and D are both correct, have the correct understanding that basically when you do a scatter, as long as the send buffer is the same size, has the same amount of data as the receive buffer, you're okay. Yeah. So you'd think that D would be right. The types and characters are the same in length in bytes. However, technically, if I had a scatter, if I did a send buff of 2 integers and a receive buff of 1 double, technically MPI could complain, say, look, the send type and the receive type don't match. 2 integers doesn't match 1 double. In practice, it probably doesn't. So D is probably correct in practice, although in principle it's incorrect. The real is D. The types can be different, provided at least one of them is an MPI derived type. So, for example, if I created a compound type which was 2 integers, so the send buffer was 1 compound type, but the receive buffer was 2 integers, they would match because the buffer contained 2 integers. So as long as the buffer has 4 integers or 8 doubles, it doesn't matter how that is specified. And that's almost D, but slightly subtly different. Technically, MPI requires that the contents of the message are the same. If you're sending 8 doubles, you need to receive 8 doubles. You could specify the 8 doubles in different ways. However, in practice, D is probably true. In practice, it probably works if there's the same number of bytes in there. So most people got that right. That's good. So final question, just as a final one. So this formatting has gone all wrong. So they've updated. Okay, they've updated this quiz since I last used it, and this is formatted incorrectly. So apologies about that. I will fix this up. Okay. You're seeing the. Okay, fine. Okay, I'm seeing the instructor version, not the. That's good. Thanks for telling me that. Fine. I'm seeing the instructor version, and you're seeing the. Fine. So basically, the even processes call MPI reduce, and they add their rank up and store the answer in even sum, and the odd processes call MPI all reduce, but they store the result in odd sum. What's the output of it? So the sum of the first 4 even numbers is 12, and the sum of the first 4 odd numbers is 16. Yeah. So that's where these numbers come. So this is the final question. It's just for a bit of fun. I said, if you don't know, just have a guess. So if I just check, I've lost my place. Okay, so if people are sorry, I'm in the wrong window. Apologies. I again got myself confused. Okay, so this is the closest thing I have to a trick question. The answer, looks like it's even sum is 12, odd sum is 16. That's However, the answer is being actually almost half of you got it, which is pretty good. It's not if someone who answered So the question is written to make it look like the answer is C. I appreciate that. So if you answered B, why do you think? So the question is written to make it look like the answer is C, but the answer is actually B. Anyone want to answer? You know, if you answered B, why? So I'm just interested because that's the correct answer. I just wondered what the logic was. Yes. So yes. So all reduce means all all of the processes. So all reduce is a reduction across a group of processes, and that group of processes here is MPI world. So actually, all the processes are participating in the same all reduce. If we didn't have the else, if we said, what would happen if we just had if rank %2, what would happen if we just had that? So what if we just had if rank %2 equals 0, MPI or reduce? What would happen if we on MPI world? What do you think would happen if we just had that? So we just have the first branch. If rank %2 equals 0, which is half the processes, MPI will reduce rank even sum 1 MPI into MPI sub MPI world. What do you think would happen if we did that? So half the processes are calling MPI or reduce. There would be deadlock, exactly. Because those processes are sitting in there saying, right, I'm calling MPI or reduce, and it's on MPI world. So I'm expecting all the other processes. I'm going to wait till all the other processes arrive, okay? And the odd process is never going to arrive, so it will deadlock. It will wait forever. So 99.9% of the time you call all reduce, all the processes are executing the same line of code. But all that actually MPI cares is that all processes call the all reduce. The fact that they come from different lines of code is irrelevant. In fact, how would the MPI library even know what line of code it's coming from? It just knows it's been called. So how would you? So you're absolutely right. These processes are all participating in the same all reduce, and it just happens the even processes store the result in even sum, and the odd processes store the result in odd sum. But it's the same sum. It's the sum of all the ranks together. How would you achieve the even odd split? How would I have the even processes add up their numbers and the odd processes add up their numbers? How would I do that in MPI? So you can't, this doesn't do what you think it does. If you wanted to do that, I want the even process to do, yes, so you need to do two separate communicators. You'd have to create an even com and an odd com and split, because the reason that collectives take a communicator as an argument is to allow you to do subsets. So that's good. Okay, fine. So hopefully you thought that was interesting. I will stop the quiz, and hopefully that just give you some background. We can start chatting about MPI. Well, I'll just briefly show the timetable again. Wait, can you see? No, I'm not sharing this screen, so yeah, so we're going to do training. So where are we? We're slightly okay. So I actually take I will give the MPI history talk very quickly. It's and then we'll have a coffee break, and then after the coffee break. So when there's no practice, we'll have a brief lecture, and then there's a practical on point-to-point performance. So I might be slightly over time on the MPI history, excuse me, but hopefully it's reasonably interesting. So I have it here. So let's just get this set up. Again, if you have any questions, please So, Sherm, that's a very, very good question. So, in MPI speak, asynchronous functions are blocking. However, they achieve the same thing as non-blocking communication. So MPI's terminology for synchronous, asynchronous, blocking, non-blocking is, I mean, MPI was written over 30 years ago, so it's maybe not the terminology we use now. But blocking means, so a blocking function in MPI only returns when it has completed what it was supposed to do. Okay, when the operation is completed. So when I call an asynchronous function, you call it. So let's say I call MPI send. I call MPI send. MPI does what it's supposed to do. It buffers the message and returns to you. So technically, it's a blocking function. The function will block until it has completed its operation. However, for a buffered send, that operation is just copy the message to a buffer. So technically, asynchronous functions are non-blocking. However, they achieve the same thing as non-blocking communications, that they avoid deadlock. So that's a very good question. It's a slightly subtle one. However, you would never call. There's no need to use non-blocking forms of asynchronous functions because you're just double counting there. Does that make sense? It's a very good question. It's slightly technical in MPI. Technically, asynchronous functions are blocking, but they achieve the same as non-blocking calls. Okay, that's a very good question. So if I share this PowerPoint, so I'm going to briefly talk about the evolution of MPI. A very brief history, and I've sort of this is just to set the standard. I mean, it is remarkable. MPI has been around for over 30 years. I actually met at a social event about 7 or 8 years ago, somebody from EPCC who had been involved in the development of the MPI standard and writing some of the first MPI libraries. He had subsequently moved on to another completely different career. He was astonished that people were still using MPI 30 years later. Okay, but there you go. So the important point is, before MPI, there were lots of message passing libraries. So in the late 80s, early 90s, if you bought a parallel computer, you had to rewrite your program because most computer vendors had their own proprietary libraries. There were some portable libraries, but they're very much academic, done by academics as research exercises, and didn't really address portability and such like. Different libraries use different models of communication. So some libraries default model of communication was synchronous, others default model of communication was asynchronous. Some had a pipe model. This made application development very hard. So what you had to do in the late 80s, early 90s, was that when you developed an application, you have your own communication library, which did what you wanted, send or receive a message, and then implement that library using whatever was available on your platform. And MPI was an attempt to define a standard set of communication calls. And one of the reasons why MPI has been successful, I think, is that it was based on experience. People didn't just write the standard out of thin air. A lot of people had made a lot of attempts at writing message passing libraries, and so to a large extent, MPI was best of breed. You know, what works best. Okay. So the main website is here. It's controlled by the MPI forum. There's representatives of a lot of vendors and academic library developers. That's one of the reasons the specification is so large. For example, why does MPI have MPI send when nobody uses it? Well, PVM's method of sending messages was asynchronous with explicit copying, and so that was supported there. A lot of the specification is driven by the library developers. What they're saying is, don't tell me how to do something, tell me what you want to do. So MPI typically just says, could you do an all reduce, but don't mandate how it's done. And this leaves a lot of scope for optimized versions on different hardware. So this is deliberate. Many aspects of the specification allow freedom in the implementers to do what they want. So often people ask, what is MPI doing here? Well, you're saying, well, it might be doing this, it might be doing that. I might have a mental model of what it does, but there's no guarantees. And this makes it very easy to port or optimize MPI for new hardware. You will presumably have some default implementation of various routines, but on a particular system, you are free to override those and implement something more efficient. However, the flip side is that just because your MPI program works correctly doesn't mean it's correct. It's just like you write a program in C or Fortran or C++, just because it compiles and runs on the GNU compiler does not mean it's a correct program. There may be some ambiguities, or you may be relying. It's a classic thing in a C program. You do int I, yeah. Is I initialized to 0 or not? Well, it's not guaranteed to be initialized to 0 by the C standard. However, a lot of compilers may do it for free, but you must not assume that. The early history here, it's an API. It's not a piece of code. It's a definition of a library, and there are many implementations of the MPI spec. Well, I say many. Like all these things, there used to be many, and now we're coming down to a few. There used to be many hardware vendors. There used to be many operating systems, and now there's 2 or 3 hardware vendors and 2 or 3 operating systems. So, however, there is more than one implementation of MPI. There's Intel MPI. A lot of people use MPI-CH or OpenMPI. Various vendors like HPE may have their own optimized implementation. The work started in 92. MPI is about, we should have a party. It's 30 years old. MPI version 1 had the basic point, and most MPI programs now don't use much more than was available in the MPI standard in 1994. About 3 or 4 years later, they went back and wrote MPI+2, which included parallel I/O, remote memory access, dynamic processes, and it added a C++ interface. And so then it was fairly stable for 10 years, okay? Although they have removed the C++ interface. There used to be a bespoke C++ interface, which had a kind of object-oriented model where the send and receive operations were methods on a communicator object. But it became, the C++ standard has exploded, and it became far too much work to support that. So now MPI is support. You can call MPI from a C++ library, a C++ program, but you have to realize that it's just to MPI, to C++, MPI is a C library. But basically stable for about 10 years, and then in the mid to late 2000s, hardware started to change a lot. We got much larger computers. We got multi-core computers. Things got a lot bigger, and so there have been a few things added to MPI since the early mid 2010. Neighbourhood collectives, which I'll talk about. There's something called the unified RMA model, which is to support shared memory processes. I'll talk about that. And there's new things like persistent. So there has been a few changes, but MPI has largely been static, fairly static for a long time. I'm just going to overview a few things which we'll come back to. MPI2 one-sided communication is an attempt to allow you to basically read and write data, to write data direct to a remote process or read the data directly from a remote process. These are often called put and get operations. Although this is MPI, I would say it's not message passing. Message passing is based on send and receive. But anyway, it introduces things called this is implemented in MPI, but allow you to create memory windows, a chunk of local memory that will be accessed by remote processes. So I'm not going to go through this. I'll go through this quite briefly tomorrow, but I'm not particularly a fan of this model, but it does allow you to do something in MPI, which I think is useful, which is for MPI processes to have shared arrays similar to OpenMP on a node. So, but this MPI do one-sided communication, something you may not have come across. It is quite complicated. It's quite bloated in the standard, but I will touch on it because I think it does have some aspects of it which are useful in real programs. MPI 3 introduced quite a lot of new features. introduced non-blocking collectives, which I'm not going to talk about particularly, but I can mention it. Introduced neighbourhood collectives, which I will talk about, which are very interesting. It improved improvements to the one-sided communications, which I'll mention briefly. It also had a new tools interface and new bindings for Fortran 2008. Actually, so I'll maybe just do a quick quiz here, because it'd be useful to know. I'll do a quiz at the end. I shall. Sorry, I've managed to mess up my I'm going to ask about programming. So I just want to get. I didn't know if people are C, C++, Fortran 90 or Fortran 2008 type programmers, where I'll allow people to self-identify as their Fortran knowledge. So yeah, for a C programmer, MPI is quite straightforward. For C++, again, MPI is available, but it is a C library. So there is no C++. There's no supported C++ interface. So you have to use like a C library. Fortran. The nasty thing about MPI is that technically it's illegal Fortran. MPI has a send routine which takes a buffer of any type. There's no MPI send int, MPI send float, MPI send real. There's an MPI send routine, and you pass the type parameter as a flag. That is technically illegal Fortran. So MPI was always on a bit of a sticky wicket with Fortran 90. There is a new Fortran 2000, well, I say new, 10 years old. There's a Fortran 2008 interface to MPI which solves all those problems, because Fortran 2008 has a way of interfacing to C. So that's all fixed now. Anyway, I'm just interested in these, in that. That's useful to know as a background. Thanks. So there's a new tools, a new binding to Fortran. So the binding to Fortran 2008 was fixed in MPI 3, although many people still use the old Fortran 90 bindings. There was a few basic, and in MPI 3, the C++ language bindings were removed because it was too much of an effort to support. There were non-blocking collectives added to MPI 3. They're very simple extension. Instead of MPI bcast reduce and or reduce, you have MPI ibcast I reduce I or reduce, which means that they return immediately. And just like any non-blocking routine, you get a handle, a request object to wait on. I'm not a fan of these, but they're there. I've never found them particularly useful. What I do find useful are the neighborhood collectives. These I will cover these later on, but they basically, MPI has always, since its inception, had the concept of topologies. You can tell MPI, my process is arranged in a 3D grid. However, MPI never took full advantage of that, because there was never a routine to say, send a message to all my neighbors. All you could do with these MPI topologies is find out who your neighbors are, but then you just had to do point-to-point send and receive, which is a bit annoying. These new neighborhood collectives really leverage the full power of MPI topologies, things like Cartesian topologies. And you can create a Cartesian topology, tell MPI, my process is arranged in a 3D grid, and then you can tell MPI, please send and receive a message to all my neighbors. So you can implement halo swapping, the 3D grid, in a single MPI function call, which is really quite nice. So I like the neighborhood collectives. I think they're useful, and I have used them in practice. I'll talk about these later on, but there were lots of changes to the one side. The MPI one-sided have a rather checkered history, but I will basically, there is a way now to have shared on a single MPI node, on a shared memory node, sorry, on a single node in an MPI program, processes on a node can now share memory for direct read and write, exactly like OpenMP can with their shared arrays. And I will cover that because I think it's a useful feature. There are things called persistent collectives, which I'll very briefly cover. So the idea, there was a slightly bonkers. If you call an MPI or reduce in an MPI program, 99% of people will call the same MPI or reduce a million times. You'll call it with the same input parameters and the same output parameters on the same communicator. There was no way previously to tell MPI that. I'm going to call this all reduced, and by the way, I'm going to call it a million times. Because if MPI knows you're going to call an all reduced function a million times, it could say, well, I'll go away and spend a bit of time finding out what the best way to do that all reduce is. Now there are things called persistent collect. You tell MPI, here's a collective function, and by the way, I'm going to call it lots of times. And that allows the MPI to go away and spend a little time working out what the best way to do it is so that it does it efficiently. There's also got something called partition communications, like I'm not going to cover them, but the persistent collectives is a useful extension. There are the MPI5 working groups were set up. This slide might be slightly out of date, but it was talking about application binary interface. There's a big problem now that MPI is standard at the function prototype level, but not at the binary level, which means if you compile a program with one MPI library, you can't link to another. It would be nice if you could, and they're trying to standardize that. Fault tolerance, people have been talking about fault tolerance for years. I don't think it will ever come. I don't think MPI can have fault tolerance. I don't think it's possible, but people keep looking at it. They're trying to look at more hardware and virtual topologies. And talking about more hybrid like and accelerator stuff. Most large parallel computers now have accelerators like GPUs. MPI isn't really aware of them. Languages, a lot of people program in Python. There are interfaces to MPI for Python. They're not standardized. Again, they're still trying to look at the RMA, remote memory access stuff, which is to do with put and get, direct read and write. It's awkward. Again, in my mind, it's not message passing. And sessions, I can't quite remember what sessions are. We'd have to look at that. But there is a stuff on the website, a list of the working groups, so okay, fine, yeah. Make it more so I can actually just share. You can look at that's going on. So there's still MPI is still ongoing in its development. Sorry, for some reason my slide is not working. There we go. There are many different implementations of the MPI specification. Many of the early ones were ported. There's really two main open source MPI implementations, MPI-CH and OpenMPI. And a lot of vendor MPI implementations are based on these. So for example, if you're HPE and you have the ARCHER2 system, it has a bespoke interconnect, the slingshot interconnect. What you would do is you would take an open source MPI like MPI-CH and optimize some of the low-level functions so that they work well on your interconnect. You don't rewrite the whole thing, you optimize some low-level functions. This is a very out-of-date sort of MPI-CH rock family tree, but there used to be lots and lots and lots of stuff, but development is really focused around now OpenMPI and MPI-CH. I have to say OpenMPI is a really stupid name for OpenMPI. So people who developed a bunch of MPI implementations got together to develop an open source version of MPI. At that point, OpenMP, which is a compiler-based way of doing threaded programming, already existed, and they should not have called it MPI or OpenMPI. The amount of confusion that caused, because OpenMPI and OpenMP, despite this being a difference of one letter, are totally different things. OpenMP is a set of directives where a compiler can implement thread-based parallelism. OpenMPI is a library which implements the MPI message passing library. I really wish they had called OpenMPI, but they did. That's annoying. So MPI+CH is virtually the default MP implementation. It has a lot of support for generic clusters, and a lot of vendor MPIs are based on MPI+CH. It's had a bit of a history, but the way it works is, there's a lot of code in MPI, but basically at the end of the day, you have to be able to send some number of bytes of data from one process to another. So the way that MPI+CH is portable is they have a low level they call the abstract device interface. So basically, to run the MPI+CH on your new hardware, you have to implement a very small number of low-level functions which are encapsulated in this interface, the ADI, which basically has very basic functions like start up a process, send 50 bytes from this process to another. So there will be some default implementations, but you can override them. So for example, on ARCHER2, presumably they've written their own implementations at this ADI level to leverage the bespoke capabilities of the slingshot interconnect. OpenMPI was a collaboration between a bunch of people. It's very active. It had a very initially it had a focus on fault tolerance and heterogeneous communication. That's maybe not so interesting now, but it does have good support for InfiniBand as well. InfiniBand is a very popular sort of mid-level interconnect. You'll find a lot of HPC clusters, and it's active. It's an open source project with large and varied community efforts. So again, it's useful. On ARCHER2, we'll be using the Cray MPI, which is supplied on HPE platforms, but it's a derivative of MPI+CH. So just a very brief summary. Most MPI implementations use a common superstructure. There's lots of lines of code to do with all the stuff, and so there's hardware agnostic stuff. But as soon as we're talking about hardware dependent stuff, there's this thing called the abstract device interface, and a manufacturer will implement those functions for their particular code. So to optimize for a particular architecture, you just have to rewrite a small number of low-level communications functions. And for example, you will optimize the collective. So there will be default implementations, say in OpenMPI or MPI+CH, of how to do a collective operation, but they will be based on message passing. You might have an all reduced based on some hypercube or tree-based algorithm, but fundamentally it will be sending and receiving messages. However, you may have an interconnect like the slingshot interconnect, which can actually natively do an all reduce. So although you may, in your mind, think of all reduces being implemented through message passing, there's no need for that. All they have to do is do a global sum, and that might call directly to some very low-level hardware functionality on the slingshot network, which will give you very fast performance. And that's a deliberate design choice of MPI to allow people to implement functions efficiently. Also, modern MPI libraries are aware of shared memory nodes. They will have optimizations to speed up the node local operation. And we will see in the first exercise that send receive is much faster on a node than off a node. And that requires you to have multiple implementations of the ADI. You will have an abstract device interface to send data between process A and process B. They will have different implementations depending on whether process A and process B are on the same node and therefore share memory, or on different nodes, in which case the data actually has to go over the network. So, okay, I'm sort of bang on time. That's the end of that talk. What we're going to do, if there are no questions, I think I saw a question, but hopefully I answered it. Yes, I did. We're going to have a brief coffee break now. Coffee is not provided, unfortunately, and we'll come back at 11:30 when I'll talk about point-to-point. Hopefully you've already seen from the quiz that the semantics of point-to-point are actually slightly more complicated than you might have imagined, and actually the implementation of point-to-point, although it's actually possibly slightly more complicated than you'd imagine. So understanding the way that point-to-point works is really quite important, and we have an exercise to do. So we will do a basic ping-pong test. How long does it take to send messages between process A and process B? But hopefully, having attended the point-to-point performance lecture, you will see that the behavior of that is maybe not as simple as you thought. There are various thresholds, and by understanding the way libraries are implemented, at least in a generic sense, the different protocols that might be used, you can actually understand why there are these thresholds. So so I'm going to take a break now, but I'll be back. I'll be back here. If you haven't, you'll have been invited to apply for an ARCHER2 account. Please do so to allow you to do the exercises. But I'll speak to you again at 11:30 PST.